The trace will look something like this. I know there's a lot of information and it's easy to get lost in all of this, so here are some tips to make it easier to use. So now you should be looking at all of the main thread activity that occurs during the interaction. Sometimes there's not a lot going on, but other times it's really long and spindly, which is how it gets its name, the flame chart or the icicle chart. Okay, so once you've found the code responsible for a slow interaction, how do you fix it? There are basically three approaches. Do it faster, do it smarter, and do it later. Hi, everybody. So we all know that web performance matters, right? We all hate slow websites. And we can imagine what a user does or doesn't do on a website when it's so frustratingly slow. They leave. They don't read your article or buy your product or see your ads. They leave. Slow performance is bad for business. So then why is it that only 46% of websites have good core web vitals on mobile? To be fair, that's a few points higher than it was last year, but why is it still so low? What's holding us back? I think about these questions all the time, and there are definitely a lot of factors, from affordable hosting and our over-reliance on JavaScript to skill gaps and competing priorities. But since we're all here to talk about tooling, let's talk about tooling. Nowadays, it's so easy to plug a URL into a tool like PageSpeed Insights, and within seconds, you can see how fast or slow the page is, according to real user experiences. Scroll down, and the Lighthouse report will give you a big old score along with a list of things to improve. And boy, do people love to obsess over the score. But here's the thing. Lighthouse may only spend about 10 seconds looking at how your web page loads. It's not following a critical user journey. It's not logged in. It's not clicking on stuff or interacting with the page in any way. It's an incomplete view of what a real user would experience. And that's kind of by design, though, because you, the site owner, haven't told it anything about your site other than the URL. That's where DevTools comes in. With DevTools, you're in the driver's seat, scrolling around, clicking on things a real user would when they would. By emulating users' behavior, network, and CPU, you're able to experience the page for yourself while getting a much clearer look at where things can go wrong in the real world. But if you've ever used the performance panel, you'd be forgiven for feeling a bit overwhelmed. What you may not realize, though, is that the Chrome DevTools team has been working really hard to tackle this problem, and a lot has already landed or is being actively experimented on. So let's see what's cooking. Largest contentful paint, or LCP, is a metric that measures how quickly the page loads. Of the three core Web Vitals metrics, this is the one that sites tend to struggle with the most, which makes it a great place to start because chances are that you've had a problem with this before. So let's take a look at how we can use DevTools to measure and fix LCP issues. And I have some good news for anyone who's ever felt intimidated by the performance panel, because this is what you'll now see on the new landing page. There's no need to record a trace or anything, just open up DevTools, and there's your LCP value. We can see that it's an image, and its load time is just over the 2.5-second threshold for a fast experience. But keep in mind that this is just your local experience. How do you know that that's what most other users are experiencing too? And that's where field data comes in. By enabling real user data from the Chrome UX report, you can compare that to your local experience side by side. Now, it should be really clear that other users are having loading performance issues too. And it actually tends to be even worse than this one. So to get more realistic results, DevTools will also use field data to suggest when you might need to emulate a mobile device or otherwise slow down your network or your CPU. Because things like viewport size and device speed can and do have a huge impact on what the LCP element is and how quickly it loads. So now, once you've locally reproduced a comparably slow LCP, DevTools can help you understand why it was slow. And to do that, I wanted to show you a couple of really useful features that will be launching soon, if it's not already there for anybody watching this on the recording. But to use it today, just go to the DevTools settings, enable the annotations and insights features, and record a trace. And this is what you'll get. Again, this is just an experiment for now, so things might change, but in the sidebar here, you can see a breakdown of why the LCP was slow. What proportion of time was spent waiting for the first byte of content from the server, waiting for the image to start loading, waiting for the image to finish loading, and waiting for the image to be displayed. Also, notice how each phase is visually annotated on the timeline. While the time to first byte could be faster, what really concerns me is the delay before we're even able to start loading the LCP resource. That's where the LCP request discovery insight comes in handy. It'll point out when best practices aren't being followed, similar to what you'd get in a Lighthouse audit. So far, it checks to make sure that your LCP image is discoverable in the document, which means it's not client-side rendered or deferred with lazy loading. It also checks that the image is requested at a higher priority than the default, which is low. These are really important optimizations because LCP images that are both discoverable and prioritized will have much lower load delays. This brings me to another really powerful feature of DevTools that I don't see talked about enough: local overrides. DevTools lets you modify everything from HTML, CSS, JavaScript, and even HTTP headers. You can basically test drive changes without having to deploy your website or start up a development environment. So if this page is lazy loading its LCP image, causing a high load delay and a slow user experience, you can edit it out on the fly. And now, if you rerun the same tests as before, you should see the lazy loading warning go away and a measurable LCP improvement. Now, 2 seconds is certainly a respectable load time. It's well below the 2.5-second threshold. But what if I told you that it's possible to squeeze even more performance juice from this already fast load time? So let's look at a couple of ways that DevTools can help us achieve LCP values of more like 100 milliseconds or less. There are 2 web performance tricks that we haven't talked about yet: restorations and speculations. You can think of them like optimizing based on where a user has already been and where they're about to go. A restoration takes place on a page that a user has already been to, it's already been loaded and rendered, and serves it back to the user upon request in its already finished state. And a speculation takes a page that we think the user is about to navigate to, and it prefetches and pre-renders all of that content in the background. History restorations are made possible by the browser's back-forward cache, or bfcache. You can think of it like taking a snapshot of the page as soon as the user navigates away and storing it locally in memory for later. If the user eventually clicks the back or forward button to return to that page, the browser can simply paint the same pixels exactly where they were, with no need to ask the server for the content or run any JavaScript. And this is a huge deal, because 1 in 5 navigations on mobile are back forward. And with mobile performance being especially slower than desktop, converting these slow navigations into instant ones can be an incredibly effective way to improve performance. So here's how DevTools can help us get our pages ready for bfcache. It's not actually in the performance panel, but under the application panel, there's a bfcache test that will perform a back-forward navigation and report what, if anything, prevented the restoration. And with that info, you can use the old overrides technique to fix the issue locally and rerun the test to be sure that it works. The second trick for instant navigations is to speculatively pre-render the next page a user is about to visit. This is made possible with the Speculation Rules API, which is available now in Chromium-based browsers. A speculation rule is an instruction to the browser saying which links to pre-render and when. You do need to be strategic about it though, because you can only pre-render so many pages at a time, and you do not want to waste resources. For the lowest risk, best chance of success pre-rendering the next page, check your analytics. See if any one link stands out. Maybe that's the primary call to action or the top result on a search page, and then you can write a rule to eagerly pre-render that page as soon as possible. A much safer option is to pre-render a page when the user gestures that they're about to click on a link, like on hover or pointer down. In this case, because the pre-render happens so much closer to the click itself, the navigation may not always be instant, but it's still an easy win. If you're looking for a quick and easy way to experiment with adding pre-rendering to your site, you can use another DevTools feature called snippets. This code snippet follows the same low-risk guidance to eagerly pre-render a single high-probability next page, as well as a more dynamic and moderately conservative next page. Running it will inject the speculation rules onto the page, so when you perform a navigation and reopen the performance panel, you should see much faster navigation times. So we just looked at a simple example of a dynamic rule to pre-render any page using a wildcard pattern, but speculation rules can be much more complex. You could also match on anchor elements by specific selectors, match on rule negations, or combine multiple rules. Here's a more complex example from my personal WordPress blog, which uses the default rule set from the speculative loading plugin. It's able to ignore admin-specific links, as well as any other link that looks like it should not be pre-rendered, anything with a rel equals nofollow attribute or a no pre-render class. Testing and debugging these rules requires specialized tooling. And in DevTools, there's a speculative loads tab in the application panel, where you can see what rule sets are active and the pre-rendering status of all matching URLs. As you load and interact with the page, you can watch how different URLs light up when they're pre-rendered and ready for an instant navigation. You can also use this panel to debug failed pre-renders. One common reason that a pre-render will fail is if the server responds with anything other than a successful status code. And also be aware that for pre-renders at moderate eagerness, Chrome only saves the 2 most recent pre-renders so that the user might mouse over a few new links and then the first ones will get evicted and appear as failures. Now we get to the bread and butter of the performance panel, which is optimizing runtime performance. As a quick refresher, when the browser needs to perform some kind of work, like handling an interaction, executing the contents of a script, or updating the UI, that work takes the form of a task that gets run on the main thread. And I say the main thread because there really is just a single thread on which all of that JavaScript processing and layout work happens. So for the UI to feel responsive, any tasks that need to run should execute in under 200 milliseconds. Turning back to the live metrics view of the performance panel, the same way that we calibrated our local environment to catch loading performance issues, we can enable CPU throttling to monitor for interaction responsiveness issues. On a fast M1 Mac like mine, I usually slow my CPU by about 20x to get close to real-world mobile performance. It's also possible to remotely connect DevTools with an actual mobile device to even more realistically measure and debug its performance. And so as you click, tap, or type on the page, you'll be able to see slow interactions logged to the performance panel in real time, with the slowest one being the page's interaction to next paint, or INP. And once you've reliably reproduced a slow interaction, you can record a trace to start debugging it. The trace will look something like this. I know there's a lot of information and it's easy to get lost in all of this, so here are some tips to make it easier to use. First, right-click on one of the track names and select Configure Tracks. Then you can deselect any irrelevant tracks that you want to hide from view and hit Finish. At a minimum, though, for debugging slow interactions, you want to make sure that you have the interactions and main tracks. Then looking at the interactions track, locate the slowest interaction. If it's not clear which one is the slowest, you can hover over each one to see its duration. Then zoom and scroll so that that slow interaction takes up the entire screen. You should see the timeline view at the top narrowed down to just a sliver. Hover over it and press the zoom button that appears to save the current boundaries. Now you'll notice the time range for your selection saved at the top as a little breadcrumb, where you can pop back up to the full timeline or repeat the process to set a nested breadcrumb. Setting boundaries on the timeline helps to prevent you from losing your place by accidentally scrolling or zooming away. Also, it adjusts the usage charts at the top so that it more helpfully lines up with the network and main thread activity below. So now you should be looking at all of the main thread activity that occurs during the interaction. Sometimes there's not a lot going on, but other times it's really long and spindly, which is how it gets its name, the flame chart or the icicle chart. Each spindle shows you the entire call stack for every function that runs, with each entry color-coded by type. Yellow for high-level JS operations, purple for style and layout work, green for rendering, gray for debugging, and all of the pastel colors differentiating the various application scripts. You might also see a red triangle in the corner of an entry. That's a warning indicator. For example, if the task exceeds 50 milliseconds or the style recalculation was forced by a script. A good way to get an overview of what's happening is to click on its root. I like to use the bottom-up pane to summarize where the time is spent. Also, I use the domain setting so I can see which application code is running and for how long. Third-party scripts, or even, yes, browser extensions, might show up in this list. Browser extensions impact page performance, both for your users and for you as you're debugging the page. So unless you're explicitly trying to debug extension performance, disable them or run your test from a guest profile in Chrome. Removing the grouping lets you see which specific functions or activities take the most time in aggregate. The self-time column measures time spent at the level of the call stack, while the total time column measures that plus the time spent in all of the descendant levels of the stack too. The slowest self-time will usually point you to the biggest area of improvement. Otherwise, the total time will lead you to the slowest ancestors within the call stack. Okay, so once you've found the code responsible for a slow interaction, how do you fix it? There are basically three approaches. Do it faster, do it smarter, and do it later. Depending on what your code is doing, you might only be able to employ one or two of these strategies, and that's okay. Whatever you can do to get off the main thread sooner will be good for performance and I&P. So let's talk about them in a bit more detail. The first one, speeding up your code, can take the form of software engineering fundamentals like code refactoring and algorithmic optimizations. There may also be some narrowly applicable web performance anti-patterns that you could fix, like reading an element's text value using text content instead of inner text, switching from synchronous XHR to asynchronous, or batching DOM reads and writes to avoid layout thrashing. But you want to know an even more effective way to improve performance? Get rid of the scripts. The fastest code is the code that never runs, right? So think about it. What are you doing in JavaScript that could be done using modern APIs instead? For example, maybe you can use CSS for animations, or the date and intil APIs for localization, or the loading equals lazy HTML attribute for lazy loading. You don't always need libraries for these things. And I actually just came across a really great example of this today. Why on earth did I ever download a package to generate random UUIDs? And if you get your documentation on MDN or web.dev, you'll see this baseline widely available badge, which means that yes, this method is supported by all major browsers, and it has been for at least 2.5 years, so it's safe to use in production, and getting rid of the library will probably help to speed up your site. All right. Once you've sped it up as best you could, the second strategy is to break it up into smaller pieces, also known as yielding. The easiest way to add these yield points in your code is to use the new scheduler.yield API, falling back to set timeout as needed. The same amount of work will happen eventually, but at least you're giving the browser a chance to provide feedback along the way. Each chunk of code should ideally take no more than 50 milliseconds on a typical device, which gives you plenty of headroom under that 200 millisecond threshold for a fast interaction. The third strategy is to defer low priority code. Yielding gives the browser a way to paint early, which is good enough for INP, but if it still takes a while to paint something meaningful, the user experience is not so good. So in addition to yield, the scheduler API also includes the post task method, which gives you a lot more control over when exactly that work should happen relative to other tasks in the queue. So if your code is a mix of different priorities, you can use post task to say, do all of this user blocking work now and do all of this other stuff later, falling back to request idle callback or set timeout as needed. For more information, you can take a picture of this URL if you really want to nerd out on task scheduling. This optimized long tasks article on web.dev will cover everything you need to know. So far, we've looked at using DevTools locally to find performance issues and comparing that performance to real user data from the Chrome UX report. But that's not the whole story. For example, how do we know that just because we found a slow interaction, it's the same slow interaction that users are experiencing? What if no one ever really clicks that button, or there's some other edge case that we haven't even considered? To answer these questions, you need to go deeper than the Chrome UX report and look at the diagnostics. This is called real user measurement, or RUM. Core Web Vitals metrics and diagnostics are openly available through a variety of web platform APIs. If needed, you could collect this information on the client side and report it through to your analytics. There are many commercial RUM tools that already offer varying levels of support for the Core Web Vitals and their diagnostics, so I'd encourage you to shop around if you're interested. But just to show you that it's possible to roll your own with free tools, here's a high-level look at a pipeline built on Google's stack. First, we collect the Core Web Vitals metrics and their diagnostics in the browser. Then we send them off to Google Analytics using custom events. And on the GA side, we configure it to write these events to BigQuery on Google Cloud, where we can process the raw analytics data into something more usable. Finally, you can build reports to visualize and explore the data in Looker Studio. Unfortunately, I don't have time to walk through all of the code and the queries step by step, but you can check it out at web.dev/vitalsga4 for a guide to setting this up yourself. I do want to take a minute to talk about some of the tools and APIs that I think provide the most diagnostic value. For starters, the best thing that you can do is include the web-vitals.js library onto your page. It's an open source project maintained by the Chrome team, and it's the industry standard way of measuring Core Web Vitals. It has two builds, the standard build that reports on the Core Web Vitals metrics performance itself, and also the attribution build that also includes diagnostic information about each metric. Using the attribution build, you can get a ton of valuable data out of the box and augment that with additional information from the web APIs. In addition to the obvious stuff like the value of the metric when it occurred, its subpart times, web-vitals.js makes some of the underlying API entries available as well. For LCP, you can use the navigation timing entry to extract more granular data on the backend load time. For example, how much time was spent doing redirects? And also the not restored reasons API to help explain why a back-forward navigation didn't use the bfcache. For INP, you can use the long animation frames API entries to understand what the main thread was doing at the time of the interaction. And here this code summarizes what kinds of scripts were running and for how long. For example, this might give us a clue that the interaction was blocked for most of the time on callbacks instead of the event listener itself. The long animation frames API is really, really detailed, so you could go deeper on additional diagnostics, like what kind of callback was it? Was it an intersection observer or a set timeout? Which script added it? And even the name of that callback function. So here's an example of what you can do with this data. This is a dashboard that I made for the web.dev website based on a very similar pipeline. And using something like this, you can identify some of the most common reasons for slow performance. It's almost like a Mad Libs game, where you can fill in the blanks using real user data to create reproducible test cases that you can then take to DevTools for debugging. I like to start with the big picture of how INP is performing over time, how it's distributed, and how it varies by page type. The learn pages are especially popular, and they're among the slowest pages. So after I filter down to just those pages, the next place I look is at where that time was spent. I know this looks kind of chaotic right now, but if you look at the INP phases at the top, notice that input and presentation delay tend to be the slowest phases rather than the processing duration itself. Another thing you might notice in the bubble chart at the bottom left is there really isn't any one script type that stands out as both popular and slow. So this suggests to me that it's more that the page is very busy rather than the interaction handler itself being slow. The last place I'll look is at the interaction target. What exactly are mobile users interacting with to get such slow experiences? What you'll see is that these slow interactions tend to happen when the users are tapping on plain text, like the section headers or the paragraphs. Side note, yes, text can be interactive, like if you're trying to select it, and it should also be fast. So this corroborates the theory that the interaction handler itself is probably not the bottleneck. And putting all of this together, here's my Mad Lib. It seems like mobile users on the Explore pages tend to have slow INP caused by input and presentation delays when they're tapping on text content about 5 seconds into the session. Well, now I know where to look. I can fire up a performance trace under those conditions and get to work. And here's what I found. A slow interaction with high input and presentation delays bogged down by a cascade of style recalculations. At first, I had no idea what was responsible for all of that work or why it kept repeating itself. But things soon became clear when I inspected the DOM a bit more closely. These slow style recalculations were caused by 31 infinitely looping CSS animations. Spinners. I know I said earlier that it's faster to use CSS for animations, but not like this. The bug was simply that the spinners were never stopped animating, even after they were hidden. Thankfully, it was an easy fix, and I'm happy to report that it just went live on Tuesday, resulting in an INP improvement of about 25%. So the performance panel is an incredibly powerful tool, and you do not need to be a performance expert to start using it. The DevTools team is actively working to ship new features in just about every Chrome release to make the panel even more powerful and easy to use, with a lot more still in development. So give it a try and let us know if you have any feedback. And by adding field data to your tooling workflow, either from the Chrome UX report or whatever your RUM solution may be, off the shelf or homegrown, you can be sure that you're fixing performance issues that are actually affecting real users. We all hate slow websites. So now let's put these performance tools and best practices into action to make the web a faster place. Thank you.
Okay, a couple of quick questions. What's the standards track / support roadmap for scheduler?
So it's being worked on right now. It's Chromium only. It's going through, I'm not sure which exactly it is, Web Incubator Community Group. Right now, post-task is widely available in all major browsers. The yield function was just actually released a couple of weeks ago in Chrome 129. But I would encourage you to check out the chromestatus.org website to see exactly what the status is of each feature.
Nice. Is there anything you'd like to see added as a new Web Vital?
Smoothness is another one that we've been looking at. Like if you've ever been scrolling and things have just felt really janky and it stutters as you're moving, that's more similar to like frames per second. It ties in with INP really nicely because a lot of JavaScript work will slow down that type of interactivity. I'd really also like to see something around accessibility. I look at performance as a type of accessibility because if the application is so slow, you really can't even use it at all. So maybe something around there, but it's really hard to measure that in production.
Mm-hmm. Well, we are out of time, but there is a really great question about Gen AI that I would like to see answered in the chat. So I'll leave that as a cliffhanger for everyone to check out. Thank you so much, Rick. And let's give him a round of applause.
Thank you.